Good evening, young people. It's Mrs. Rains. I'm going to be talking a little bit more about thermochemistry and some introduction stuff that kind of combines things together. I'm also going to talk about what we learned today, Tuesday, January 3rd, in class, doing the activity that we did and kind of wrapping that up, because tomorrow we're going to come in and participate in some other stuff. So it's going to be a little lengthy, but watch the first part, dole it out, try to get through it, okay? You have homework due by Friday. All right, so in thermochemistry, we define the relationship between a chemical reaction and the energy change involved in it. That's where we are. That's the only thing that we really are concerned with. So the focus of this energy is a particular unit that we will be talking a lot about, and that is heat. Okay, heat is the unit of energy that we're talking about. We usually talk about that in units of joules or kilojoules. So those are the two units that we use most often to talk about heat. And that's pretty much our wheelhouse. There is going to be something else involved, which you will see in just a few moments. Okay. The first law of thermodynamics. Now, in your textbook, it talks about the energy of the universe being constant. Okay, that's just a fancy way of saying that energy cannot be created or destroyed. And we already know that. You were introduced that very early on in science classes, and you know that it's the law of conservation, sorry, it's sloppy, of energy. Okay, so you already know this. You know the first law of thermodynamics. So guess what? You know thermochemistry already. But we know from the activity that we did today that heat is transferred between two objects. So Gerard and I spend a lot of time with this because Gerard, let's see if I can find a nice color for him. I don't have a color for him, so I'm going to make him gold. Okay, Gerard's hand. I'm not a very good artist, so don't go there, okay? And then my hand, I am going to make this light blue color. Why? Because I can. Okay, so my hand is always cold, and my husband's hand is always hot. So when we shake hands or when we touch hands, I'm actually taking warmth from him. So everything always goes from warm to cold, okay? Everything. Whenever we're transferring heat or energy, it's always going from a warm place to a cold place. It never goes from cold to warm. It's always traveling from warm to cold. So we have to be aware of this as we're talking about it and as we're discussing it. So the other thing that we need to talk about are the relationships and equations that we dealt with today. So I want to talk about a whole nother equation for just a second, because I want you to see where I'm at in this whole process. So science is full of equations that were developed by looking at experimental data. And actually your freshman year, if you had a pretty decent teacher, you saw this demonstrated. There was an activity where you had a cart and a bendy ruler, and you put clay or boxes of clay or heavy stuff on the cart, and you pushed it, and you saw how fast it would go with the clay and how fast it would go without the clay with the same amount of push. And you did all of this. Well, why did we do all of that? Well, we did it because we wanted to find out Newton's law relationships, and Newton actually probably did this himself. So let's look at this. Force is equal to mass times acceleration. If mass is held constant, then as force increases, acceleration increases. If force decreases, then acceleration decreases. If force is held constant, if mass increases, then acceleration has to go down, m times a. If mass decreases, then acceleration has to go up. We talked about that when we were talking about the particles in the gas law section, and how we could deal with that. So if acceleration is constant, if force goes up, then mass goes up. If force goes down, then mass goes down. Well, what do we know about these now? So both are moving in the same direction for force and acceleration when mass is held constant. So it's a direct relationship. Therefore, force is directly proportional to acceleration. Pretty simple, right? That little schwa looking sign that looks like a fish or an alpha means proportional. So these are moving in opposite directions. They're moving in different directions. So that means it's an indirect relationship. Therefore, mass is proportional to 1 over acceleration. It's an indirect relationship. They're not saying one is proportional to the other. It's proportional to 1 over, or the reciprocal of the other. So both are moving in the same direction for the next equation. That's a direct relationship. Therefore, force is equal to mass times acceleration. So if we use this to look at the triangle, so here we go. We have these relationships, and what we see in this triangle is this. Look at where force is. Force is directly proportional to acceleration. Force is also directly proportional to mass, so it's above it. But mass is directly proportional to 1 over acceleration. Mass is equal to force over, okay? So we can see this direct relationship and indirect relationship with an equation right away when we understand the mathematical reckoning of it. So let's look at what we did. Okay, this is just showing, okay. So in question 1, we found that heat was held constant. Heat was the same. So when mass went up, then delta T went down. And if mass went down, then delta T went up. So they're moving in opposite directions. So what do we know about them? We know that they're an indirect relationship. Therefore, mass is proportional to 1 over delta T. Okay, so let's keep that in mind. So for question 2, mass is constant. So when Q goes up, delta T goes up. When Q goes down, delta T goes down. Both are moving in the same direction. So we know that Q and delta T are proportional to one another. In the next equation, or next question, we found that delta T was constant. So when Q went up, mass went up. When Q went down, then mass went down. So both are moving in the same direction. Therefore, Q is directly proportional to M. Now, if you're thinking the same way we were thinking through the force is equal to mass times acceleration, you already have an equation in mind. You remember that force was directly proportional to mass and acceleration, and it was on the other side of the equal sign. Mass was indirectly proportional to acceleration, and they were on the same side of the equal sign. So if you had to, you can probably start figuring out that Q is somehow proportional to or equal to mass times delta T, which is exactly what we used in problems 1 through 3 to get through the problem. So if we have these relationships, we can start with our triangle. Q is on top. That means mass is on the bottom, and delta T is on the bottom as well. It runs in the same direction. So we get this, Q is proportional to mass times acceleration. We're not putting equal signs yet because we haven't quite figured out all of it, okay? So then we went through, so we used this equation or this idea to then solve problems 4 and 5, where we mixed the two waters together. And we found out that the amount of heat lost and the amount of heat gained were equal, except the heat lost had a negative sign because of the delta T. So I had to make it negative to make them actually equal to one another. So negative, so we know that negative Q lost is equal to Q gained. Okay, so that's another thing that we figured out with 4 and 5. Well, then in number 6, we had a little problem because we didn't have water both times. We didn't have the same substance, and we decided that alcohol and water are not the same. As a matter of fact, if I put water on the table and I put a little alcohol on the table, which one evaporates more quickly? The alcohol is going to evaporate more quickly. Why? Because it has less attractive forces, less intermolecular forces that are keeping it together. And so it's more volatile. It will fly away as a gas. So there's something else that's missing here, something that we have to add that will equate things to one another, and it's a constant. And this is where we begin to change it from a proportionality that we see right here to an equality. Because if we can somehow make everything equal by using some constant that's specific for that, then we can have more of an equality. And so that's where we're at next. So we have this, but we're missing something. There's something that makes everything kind of work together, and that is C, or the specific heat capacity. So now we get the equation Q is equal to M times C times delta T, where C is the specific heat constant that is very specific to substances. So different substances have different constants. And basically it's describing how much energy can 1 gram of that substance absorb. That's what it's describing. So the amount of energy 1 gram of substance will absorb in a certain amount of time. And so the unit is usually either joules per gram degree. No, I'm sorry. Back it up. Made a mistake. Okay, the unit is joules per gram degree Celsius. Jeez Louise. It's been a long day, ladies and gentlemen. I'm having a little trouble. Okay. Joules per gram degree Celsius. Okay, that's the unit, or kilojoules per gram degree Celsius. Those are typically the units that we see that in. Okay, so this kind of wraps up what we did today in class and gives you an idea of where we're headed. Tomorrow we're going to be working with specific heat. So we have this equation. The addition of C, a specific heat constant, allows for proportionalities to become equalities, because now we have a constant that we're using there. The units for C are joules per gram degree Celsius or kilojoules per gram degree Celsius, depending on what you're looking at. But there are other units that we can use for heat. Joules are the one that we use a lot. Kilojoules, we use that a lot for chemical reactions because we're talking about them in terms of numbers of moles of things. Calories and calories. So what's the difference between little c calories and big C calories? And this is the deal. Little c calories are the English standard system for measuring heat. Big C calories are the calories that we consume in our food. The big C calories are the same as little c kilocalories. So they are kcals. But in terms of how we've talked about it all along, big C cals are what we look for, okay? And then we see kilocalories, which is little c kilocalories, okay? So ultimately there are two categories. We have standard American categories, calories, big C calories, and kilocalories fall in this category. This is how we talk about them. A calorie is the amount of energy required to raise 1 gram of water 1 degree Celsius. That's what we know. 1 kilocalorie is 1,000 little c calories. Kilocalories are the same as big C calories. These are the ones that are on the food label. So if we look at our food label and it says there are 230 calories in this bar right here, we see 230 right there. That means that there are 230 kilocalories in that, which would equate to 23,000 calories, okay? Little c calories. Be really careful because this is confusing, which is why in this class we will be using the System International, or the SI system. So we will be using a joule as a unit of heat. So 4.184 joules of energy are needed to raise 1 gram of water 1 degree Celsius. Okay, 1 kilojoule is equal to 1,000 joules. So this happens to be something from overseas, and you will see that on their labels, you can see that they have both. See that right there? They have 150 kilojoules and 35 kilocalories. So they are actually using the SI system in their food counting as well. So, you know, you can see that when you're going to other countries that it might be a little bit different. You're like, how do I know? Well, 150 kilojoules is equal to 35 kilocalories or 35 calories. Okay? So relating it to units, making sense of the hodgepodge of units can be hard, but it's quite easy with conversion factors. So the conversion factor is 1 big C calorie or kilocalorie is equal to 1,000 calories, which is equal to 4,184 joules, which is equal to 1.184 kilojoules. okay? It's not as hard as you think it is. Remember, all of these can be set equal to one another, so we can go from one or the other. They're all equal to another, okay? So they have infinite numbers of significant figures as well, just a reminder. So back to thermochemistry again. Point 2 in thermochemistry, if heat is being transferred, then work can be done. So we know that work in physics is always a force acting over a distance. This is the problem. In chemistry, we don't have many forces acting over large distances. It's very hard to measure. So typically, we don't consider work. There's only one example in which we consider work, and that is what we call PV work. And PV work is basically in gases only. When a gas is produced in something and it can expand that something, then we get this idea of PV work. If we don't have that ability, we don't think about work. We only think about heat, and you're going to see in just a second what I mean by that, okay? So what are we looking at when we have a reaction? We're looking at the system. The system is where the chemical reaction occurs. There's the system. This is the chemical reaction, okay? The surroundings are everything else. So these are the surroundings. Yes, I'm covering up some words. It's okay. Okay, these are the surroundings. We always talk about this in terms of the system. We never talk about it in terms of the surroundings. So we either have a situation where heat can go out of the system or into the system. And that's how we refer to it. We don't refer to it as heat going out of the surroundings into the system. We always look at the system, and it's heat going out of the system or heat coming into the system, and that's the way we deal with it in chemistry. Okay, so here we're back at this idea of internal energy is the sum of the potential and kinetic energy of all the particles in a system, and we can see that the change in energy here is equal to Q, which we've defined as heat, and W, which is work. So we can use that, especially when we're talking about gases being produced in a flexible container like a balloon. The problem is most reactions don't always involve gases, and they don't always involve flexible containers. So if they don't involve those things, we have no way of measuring the work. So if we have no way of measuring the work, then we have to talk about energy or heat in terms of something a little bit different. And that is going to be in terms of something called enthalpy. Enthalpy is the heat unit that we use in chemistry. We also use a different symbol for that. We use the symbol of H. So don't get confused. Q is heat, but H is the heat in a chemical reaction, okay? Q is heat anywhere. H is the heat of the chemical reaction. So we know that in a chemical reaction, the change in enthalpy is equal to delta H, and it's always the products minus the reactants, always. We always take the energy of the products minus the energy of the reactions, and we get delta H, and that's going to become a little bit more important a little bit later on, okay? So let's look at this idea of energy and Q and W for a second, and then we'll return back to H in just a few moments. So we have some possibilities. So in our system, we have Q being negative and W being negative. So what is the sign of delta E going to be? Well, delta E, remember, is equal to Q plus W, right? So that means if they're both negative, a negative plus a negative gives you a negative. There you go. Not hard stuff here. So what if we have Q being positive and W being positive? Well, we have a positive plus a positive. So that means it's positive. And when W is positive, the surroundings are doing work on the system. So something's happening within the surroundings that are doing something to the system. Okay, so the next possibility is this idea of Q being positive and W being negative. And you're like, well, how can I determine what the charge is? Well, it's a little strange, but you have to go back to your vector quantities. Remember, vector quantities are the size. We use the size of lines to represent vector quantities. And we can see that the Q is a longer line right here than the W. So if Q is positive and bigger than W, so a big positive minus a small negative is going to give you a positive, a smaller positive. but it should be positive in this case if we look at the vectors and compare them to one another. If the vectors are more equal to one another, then delta E is going to be 0. If the W is bigger and the Q is smaller, then delta E is going to be negative. You can see all the possibilities that could be there, okay? The sign reflects direction of the flow of energy. That's all it's talking about. So when we have a negative sign, the flow of the energy is to the surroundings. And we have a positive sign, the flow of energy is to the system. So direction is denoted. It's a vector quantity. And the negative and positive sign are showing the direction of where things are moving. So be careful not to look at these numbers in terms of negative and positive being bigger or smaller. The negative shows a direction. The positive shows a direction. The magnitude shows how much. So that's what we're going to be looking at for how much. So if I have a negative 1500 and a positive 1500, the amount of energy is still 1500, but the direction is negative positive. So one is going in and one is going out, okay? So the value reflects the magnitude or the size, how much energy. The negative and positive reflect direction. So be really careful not to look at this like you were a number line, saying that -5 is smaller than +5, because in actuality, they're both the same size in terms of energy, but one is going in and the other is going out, okay? Be really careful about that. So this is the type of work that we're going to be looking at, and the only type of work that we're going to be looking at. And you can see there's an equation. Work is equal to -P times delta V. So the change in volume, final volume minus the initial volume. And anytime you see a delta sign, it's always final minus initial, which is why delta H is products minus reactants, because products are final, reactants are initial, okay? And P is the outside pressure. So this is only about gases expanding. If gases expand, then work flows out, therefore it's negative, okay? If gases contract, then work is flowing in, therefore it's positive. Get it? We're going out, negative, work going in, positive. All right? So there are some goofy units. How do we compare it to Q? Well, we don't always compare it to Q, but we can see that 1 atmospheres times liter is equal to 101.3 joules. So that's not too bad. We have another relationship to look at. The only time we consider work in any of this stuff is when we're talking about gases in a flexible container that we can change the volume of. So be really careful here. This is the only type of work that's considered. All right? So 2 types of reactions. So let's go back to the enthalpy part because we're back to reactions, which is our bread and butter. There are 2 types of reactions. The first one is exothermic. Energy is flowing out of the system. It's going out. So we will probably demo it at some point in time in the next 2 weeks. So what do we know? We know that we have reactants here and products here. Notice the reactants, and this is energy. So over here, this is your increasing energy. So reactants have higher energy than the products, all right? So how else do we read this? Well, we see several things here. We see this hump right here, okay? That's just the graph that's showing where we have to reach. At the top, the substance that's involved at the top, or the substance that has to be formed there at the top, is called the activated complex. It's the substance that is the intermediate between the reactants and the products that has to form in order for the reaction to continue the other way. If it doesn't form, and you can go back and forth with these, we can go reactants to products and products to reactants. Okay, the energy between where the reactants are and where the activated complex is called the activation energy, because it's the amount of energy you have to add to, you have to have in order to make this reaction go. So obviously if you have a smaller activation energy, the reaction is going to be happening more spontaneously than if you had a larger activation energy. And then the final thing that we need to talk about is, where is the enthalpy? The enthalpy is the difference between the reactants and the product's energy. Remember, we talked about that a few minutes ago, right? Products minus reactants. So the only thing that we're really worried about when we're worried about enthalpy is the difference between those two. We're not worried about how it gets there or why it gets there. We've just talked about the activated complex, but we're not worried about that because ultimately all we want to worry about is the difference between those two when we talk about enthalpy. Okay? So, Why is it considered that the product bonds are stronger here? Well, it's really not a hard thing. When we have reactants here and products here, and the energy is going up here, okay? And we have to reach an activated complex here to go either direction. Well, the products need more energy to reach that complex than the reactants do. Therefore, that's telling us that the product bonds are stronger, meaning more energy is required to reach that complex to go backwards in the system. So those bonds are stronger, and that kind of makes a whole lot of sense to us. If we had a reverse situation, we could see that the reactants have less energy, so it takes less energy to get here. Bond strength is only determined by the amount of energy that is held between those bonds for chemists. So when we talk about bond strength, we talk about it in terms of that and intermolecular forces and other things, but it's about strength. It's not about anything else. So when we're talking about strength in chemistry, we're talking about the strength of the bonds. So if they're weakly held bonds that can be broken very easily, that doesn't take much energy. But if they're really strong bonds that take a whole lot, that takes more energy to break it apart. Okay, heat is found on the product side. Why? Well, because it feels hot. So reactants have more energy than the products, right? So there are the products, but the reactants had more energy to begin with. How do we balance it out and make it, instead of looking like a weird little symbol right there, how do we make them equal? Okay, how do we make them equal? Well, we have to add the heat energy right here. That makes them equal because the reactants had more energy overall. Okay, the heat value is always going to be negative. Why is it negative? Remember, the sign tells me direction. What is it telling me? It's telling me it's going out of the system. So heat going out of the system is negative. That's all it's telling me. It's directional. That's it. Okay, so in an endothermic reaction, we have something a little different happening. We have reactants right here, and we have products up here. So we have the same general species here. We still have an activated complex up here, so that's your activated complex. Sorry, my finger doesn't work as well as my pen used to. We also have an activation energy. That's the energy between the reactants and the activated complex. So this is the EA, or the activation energy of activation. And then the enthalpy. The enthalpy, remember, is the difference between the products and the reactants. So here is the delta H. Okay? So how do we know what the delta H is going to be here? Remember, delta H is equal to products minus reactants. The products are more, the reactants are less. So I got a big value here and a little value here, so that means delta H is probably going to be positive, okay? So we'll probably do a demo sometime in the next week or so. So products have higher potential energy, but product bonds are weaker. Not much energy is needed to reform the reactants. So remember, if we talk about the activated complex, the products are closer to the activated complex in energy, therefore the product bonds are usually a little weaker. The reactant bonds are the ones that are stronger because you need more energy to reach the activated complex. Okay? Heat is found on the reactant side. Why? Well, think about it again. Products were bigger than reactants. In order to make this work, all of the energy that was in the products, has to be added over here to the reactant side to make it happen. So basically, this is the one that's the hardest. Okay, you get why things feel hot. Why do things feel cold? Because when things are cold, they're taking energy from outside and pushing it in, which leaves the outside cooler because the energy is going inside. Let me let that sink in for just a second. The energy is going inside, okay? So the heat value here is positive. Again, remember, delta H is equal to P minus R. If P is less and R is more, that's not right. I mess this up all the time. That's wrong because P is not less. P is more and R is less. So if I have a bigger number here and a smaller number here, then I'm going to get a positive value. That's what we talked about when we did the graph just a little while ago. Okay, so there we are, finished today. Hope you get all of this together.